So in these next few recordings, we're going to talk about process geomorphology. And process geomorphology is focused on the physical processes which happen on the Earth, which act to change landscapes and create certain types of landforms. So why do we focus on processes? Well, to sort of demonstrate this, I'll give you an example of geomorphology without processes, which is William Morris Davis's cycle of erosion. Davis's theory had sort of a Darwinian approach to geomorphology, where landscapes evolved over time, from a youthful state to a state of old age. So what would happen is you have this rugged landscape where rivers are sort of down-cutting and forming these deep valleys, but eventually when they've down-cut to the point that they're going to down-cut, they start moving laterally and flatten out the landscape, creating a relatively flat plain called a peneplain, and when this happens, the landscape is said to be in old age. And there may be a few Inselbergs, which are isolated points of, mountains or high topography within this peneplain, but largely the landscape has fully evolved. And then, if the land is uplifted again, the whole cycle starts again, where you get a rejuvenated landscape. Now, there is some truth to this theory, in the fact that rivers do cut to a base level, just naturally. Rivers may cut to a local base level, like a lake or a reservoir or a waterfall, like Niagara Falls, for example. Or they may cut down to the ultimate base level, which is, of course, sea level. And it is true that these base levels change as either landscapes are uplifted by tectonic processes or sea level or lake level or whatever changes due to climatic processes. That said, the problem with Davis's theory is it really isn't very specific. It doesn't tell us what's changing the landscape. It doesn't explain any variation between, say, climates, for example. And it doesn't provide us with specific information like, how is this segment of the river going to move in the next 30 years? So, it does provide a model in some ways for how landscapes change, but it doesn't apply to all landscapes, and it's, not specific enough to be particularly useful. And this is why we take the process approach, because we can be a lot more detailed in terms of how things actually work, and then use that to sort of predict the future and have a better more specific understanding of landscapes. Just some examples from Davis's theory that are in the real world and, are sort of used as textbook examples of Davis's theory. One is Uluru, seen as sort of an Inselberg on a peneplain. And another is of a rejuvenated landscape on the Colorado River, where you see this old meander, and then either the landscape was uplifted, the landscape was uplifted because the Colorado Plateau is rising, and then the river shifted down to its current course, forming a new meander. So when we're talking about processes, there are two groups. One is high magnitude, low frequency events, and low magnitude, high frequency events. Low magnitude, high frequency would be, just your average everyday stream flow or maybe the odd storm. A high magnitude, low frequency event would be a massive flood or tsunami or something like that. And there is, a great debate in geomorphology which of these two classes of events are the most important. In uniformitarianism, the idea is that the same processes that we can observe on Earth today were the most important in the past as well. So these processes are the most important for landscape change, whereas catastrophism or neocatastrophism implies that the Earth is altered by these very infrequent but very dramatic, intense events. And these are the main events for forming landscapes. And there is some truth to both. Landscapes are definitely changed by the events we see every day, just slowly over many generations on a human time scale. And there are also dramatic events that change the Earth rather quickly. For example, these channeled scablands in Washington State were produced when a glacial lake Missoula, broke its ice dam at the end of the last ice age and rushed down the Columbia River and created the channeled scablands. And with process geomorphology, the focus then is always on observing and measuring what causes landscape change rather than making grandiose theories about it. This can be achieved both in the lab and in the field. And this really allows us to see landscapes as systems with inputs and outputs of both energy and matter. And this then allows landscapes to be represented mathematically and computationally, which can really enhance our understanding of landscapes and give us some ability to predict landscape change into the future. So there's a lot of physics that goes into geomorphology. We're just going to scratch the surface today. But generally, forces in geomorphology can be grouped into driving and resisting forces. Driving forces cause landscape change. Resisting forces resist landscape change. Driving forces can include gravity as well as flows of water or wind or ice. And resisting forces hold material together. These could include friction as well as cohesion, such as in the case with clay, which we discussed in the fluvial geomorphology section of last workshop, or 2 workshops ago. Landscape change occurs when driving forces are greater than resisting forces. If it's the other way around, the landscape will stay the same. These driving forces can be grouped into 2 categories: endogenic processes and exogenic processes, and they're grouped based on where they get their energy from. Endogenic processes get their energy from within the Earth. This is in the form of thermal energy, the heat inside the Earth, which in turn comes from the Earth's formation, from radioactive decay of elements within the Earth, think uranium for example, and from tidal forces acting on the Earth from both the moon and the sun. Exogenic processes are an external source of energy from gravity, for example, in the form of gravitational potential energy. The sun, which of course causes air circulation on Earth, and thus the wind, causes the formation of clouds and thus rain, and so on and so forth, and tides as well. In the next 2 recordings, we'll talk about endogenic and then exogenic processes.